Introduction to Sequences and Series. Before we look at a sequence or a series, let's define a factorial. If n is a positive integer, the notation, which looks like n exclamation point but is read as n factorial, is the product of all positive integers from n down through 1. And by definition, we say that 0 factorial is equal to 1. Let's look at an example. We want to evaluate, in part A, 4 factorial. So 4 factorial is equal to 4 times 3 times 2 times 1. It's the product of all positive integers from 4 on down to 1. So here, 4 times 3 is 12, 12 times 2 is 24, and times 1 doesn't change that. So 4 factorial is 24. In example B, we have 6 factorial divided by 4 factorial. So if we think about expanding 6 factorial as 6 times 5 times 4 times 3 times 2 times 1, all over 4 factorial, that's 4 times 3 times 2 times 1, we can see that the 4 times 3 times 2 times 1 on the top will cancel by the 4 times 3 times 2 times 1 on the bottom. So 1 over 1 is 1, 2 over 2 is 1, 3 over 3 is 1, 4 over 4 is 1. And then all we have left is a 6 times 5 in the numerator, so 6 times 5 is 30. So the answer here is positive 30. And let's go ahead and try one more time. We have 3 factorial over 5 factorial. So one of the shortcuts I would say that you can try here is if the denominator is the bigger factorial, like it is in this case, or find the side with the bigger factorial and start to expand it. So 5 times 4 times, but here instead of writing 3 times 2 times 1, I'm just going to leave it as 3 factorial, because that's exactly what the numerator is, 3 factorial. And the 3 factorial and the 3 factorial, since everything here is multiplied, those are going to cancel, leave me with just a 1. So I have 1 over this product, 5 times 4, so I have 1 over 20 as my answer. Let's move on to defining a sequence. Informally, a sequence is a list of numbers. So if you see the word sequence, that's what we should basically think of. It's just a list of numbers. Formally, the definition of an infinite sequence is that it's a function. And the notation we use is a with a subscript of n. But what that really means is like the function notation a of n. But we don't write it like that. We think about it as a sub n, because it has a specific domain, whose domain is the set of all positive integers. So the only numbers that we can substitute into n are the positive integers, 1, 2, 3, 4, 5. So the notation that we use for an infinite sequence is curly braces with a sub n inside those curly braces. That would be the shorthand notation, or we could write the equivalent expanded out version, which is a sub 1, so that's the first term, comma a sub 2, comma a sub 3, and it keeps going on because it's infinite, where a1 and a2 are called terms. And if the sequence happens to stop, then it's called a finite sequence. In this example, we want to write the first 4 terms of the sequence given the general term a sub n. So in part A, a sub n equals n cubed over 2n minus 1. So we're thinking about this as a function, basically like an f of x, except the only values we can substitute in this case to n, are the positive integers, so starting with 1, and then 2, and then 3, etc. So we're going to go ahead and start by plugging in 1. So we have a sub 1 is equal to 1 cubed over 2 times 1 minus 1. So that's 1 over 1, which does simplify to, of course, 1. And then we move on and we find a sub 2 which is substituting a 2 into every n. So 2 cubed over 2 times 2 minus 1. Well, 2 cubed is 8. And then I have 4 minus 1, so that's 8 thirds, which can't be reduced. Then we have a sub 3, that's 3 cubed over 2 times 3 minus 1. So 3 cubed is 27. And then 2 times 3 is 6 minus 1 is 5. And then a sub 4 is 4 to the third over 2 times 4 minus 1. 4 to the third is 64. And then I have 8 minus 1 is 7. So we had 1 over 1, or 1, 8 thirds, 27 over 5, and 64 over 7. And maybe we can see the pattern happening in the denominator. We are going up by 2 every time we have the odd numbers that came out of that 2n minus 1 piece. And then on the top, n cubed, so we can see those integers being cubed there. So we're going to write the first 4 terms as a sequence, so horizontally as a list of numbers, and we start with A1 first. So we always start just in order. We don't put them in order from least to greatest or anything. We just start with A1, then A2, etc. So we're going to have 1, and then 8 thirds, 27 over 5, and 64 over 7, and then dot, dot, dot. This list is going to continue on indefinitely. Let's move on to part B. Our general term is a sub n equals the quantity n plus 1 over this n factorial that we looked at earlier. So we'll start with a sub 1. So a sub 1 is 1 plus 1 over 1 factorial. Well, that's 2 over just 1. 1 factorial is 1, and that's it. So we have our first term is 2. Then a sub 2, that's 2 plus 1 over 2 factorial. Well, 2 plus 1, that's just 3, and 2 factorial is 2 times 1, so we end up with just 3 over 2. Then we have a sub 3, that's 3 plus 1 over 3 factorial. So 3 plus 1 is 4, 3 factorial, remember, is 3 times 2 times 1. So we have 4 over 6, which reduces to 2 thirds. And then our fourth term, a sub 4, we have 4 plus 1 over 4 factorial. So that's going to be 5 over 4 factorial is multiplying 3 factorial, which was 6 times 4, so 5 over 24. So in a list we have 2, 3 over 2, 2 over 3, 5 over 24, and so on. Finally, in part C, we have a sub n is equal to the quantity negative 1 raised to the nth power over 3 to the n. So here, again, we start with substituting in 1. So we have a sub 1 is equal to negative 1 to the first over 3 to the first power. Well, negative 1 to an odd power is still negative 1, so I have negative 1 over 3 to the first is 3. So I have negative 1/3. A sub 2 is going to be negative 1 squared over 3 squared. Well, this time, negative 1 to an even power is going to give me a positive. So negative 1 squared is positive 1 over 3 squared is 9. A sub 3 is going to be negative 1 to the third power over 3 to the third. Well, a negative to an odd power is still negative, so we have a negative 1 over 27. And then a to the fourth is negative 1 to the fourth power over 3 to the fourth. Well, negative to an odd, or even power, excuse me, a negative to an even power gives me a positive 1. So I'm going to have a positive 1, and then over 3 to the fourth is 81. So hopefully we can see what happened here. Our terms are alternating in sign. So that came from this -1 quantity raised to the n piece that was here that made our terms alternate in sign. So we have as a list -1/3, so our first term was negative, +1/9, -1/27, +1/81, and so on. Just a quick note before moving on, I did decide to put curly braces around my list of terms, which sometimes you'll see, and sometimes you'll also just see the list of terms without curly braces separated by commas. In this example, I want to write the general term a sub n for the given sequence. Basically, we're going to work backwards. So here in part A, we're given the sequence 1/2, 4/3, 9/4, 16/5, 25/6, 36/7, and so on. I like to start by reminding myself that this first term here is a sub 1, and then we have a sub 2, and a sub 3, and a sub 4. Basically, I like to remind myself of the index, because when I substitute in 1, and I'm going to just think about the numerator and denominator separately. When I substitute in 1, that's got to give me the number 1. And then here, when I substitute in 2, that has to give me the number 4. And when I substitute in 3, that has to give me the number 9. So what I kind of like to think about to try to find the pattern is how it relates to the subscript value. So here, the relationship is that we're squaring the subscript value. So in other words, 1, that's 1 squared. 4, that's 2 squared. 9, that's 3 squared. 16, that's 4 squared. So that's how the numerator of our terms is related to the subscript. I'm squaring that value every time. So if I start to write out my general term, a sub n, well, the numerator is going to be n squared. Because remember that we start by plugging in 1, so 1 squared gives us 1. Then we plug in 2, 2 squared gives us 4, 3 squared gives us 9, and we can see that the pattern does continue with those perfect squares. Now I want to think about, in the denominator, what is that relationship to the subscript value? So here I start out at 1, and then I have to get to 2. And here I start out at 2, and I have to get to 3. And here I start out with the number 3, and I get to 4. So I'm going up by 1 every time, or I'm adding 1 every time. So the bottom, I can think about it as 1 plus 1. And then 3 is 2 plus 1, and 4 is 3 plus 1, and 5 is 4 plus 1. So again, I'm relating it to that subscript, and then basically that value gets replaced by n. So instead of 1 plus 1, 2 plus 1, 3 plus 1, the generic term is going to be n plus 1. And the best part is, I mean, we can check because we can just think about what happens when I start plugging in those positive integers. And we can see that we do get out increasing values by 1 every time with the n plus 1 term on the bottom. So this is my general term. Moving on to part B, we have e, comma, e squared over 3, comma, e cubed over 5, comma, e to the 4th over 7, and so on. Well, this first term, e, I want to think about that as a fraction, so that would be e to the 1st over 1, just to kind of really help me to think about a numerator and denominator separately. That's really helpful. So again, I want to remember that each of these numerators and denominators arise from substituting in 1, then 2, then 3, etc. So this numerator is pretty easy. We can see, well, how would I get e to the 1, and then e to the 2, and e to the 3? That would be with a general term that looks like e to the n. And the bottom is the part that we have to figure out. So I have 1, 3, 5, 7. And that pattern there is odd values. And earlier we saw how to arrive at odd values when starting by substituting in +1 and then +2, etc. So in other words, 1 can be obtained by doing 2 times 1 minus 1. And 3 could be obtained by doing 2 times 2 minus 1. And 5 is 2 times 3 minus 1. And 7 is 2 times 4 minus 1. So the general pattern here is that we're going to have 2n minus 1 as our denominator of our general term. So again, we can check a sub 1 would be e to the 1 over 2 times 1 minus 1. Well, that gives us just e. And then if I plug in 2, I get e squared over 2 times 2 is 4, 4 minus 1 is 3. So here we do have our general term. And finally, in part C, we have 1, and then comma -1/4, comma 1 over 16, comma -1 over 64. So again, that first term, 1, I want to think about it as a fraction, so that would be 1 over 1. And then I want to go ahead and try to find the pattern, how these relate to that subscript 1, 2, 3, 4, etc. Well, on the numerator, I always have the value 1, but I do have that alternating sign. So to get that alternating sign, our general term, a sub n, has to have -1, and we saw earlier how -1 was raised to the nth power, and that gave us alternating terms. But the thing is, we have to make sure that we have the correct alternating pattern, as in I start with either positive or negative depending on the sequence that I have. So here, if I start with a sub 1, which of course I have to, that's a sequence, we start with 1, -1 to the first power, well, that's going to give us a negative first term, and I don't have a negative first term. So this isn't the only type of piece that will make terms alternate. It could be -1 to the n, or it could be -1 to the n plus 1, or even n minus 1. Both of those would be fine. But in this case, if I make the numerator quantity -1 raised to the n plus 1, if I plug in 1, 1 plus 1 is 2, and -1 squared will give me a positive term. So then if I plug in 2, well, 2 plus 1 is 3, -1 to an odd power will give me a negative, so the signs alternate the way I need them to. So when we think about an alternating sequence, we might have either quantity -1 to the n or quantity -1 to the n plus 1, just depending on whether your first term is positive and then we switch to negative, or if we start with negative and then we switch to positive. So that's the numerator. And now the denominator, so I have 1, 4, 16, 64, and I want to think about how those relate to, again, that subscript 1, 2, 3, 4. So here, we want to try to basically find the pattern in these values. So I have 1, and then 4, and then 16, so, and then 64. Well, what's happening here is these are powers of 4, but the first one maybe isn't super obvious. The first one is 4 to the 0, and then I have 4 to the 1, and then I have 4 squared, and then I have 4 cubed. So on the bottom, I have the 4 to the 0, 4 to the 1, 4 to the second, 4 to the third. But I want my starting index to be 1, not 0. So here, what I want to do is write my general term as not 4 to the n, because if I have 4 to the n, then the first thing I'd plug in is 1 right here, and 4 to the 1 is 4, and I don't want 4, I want 0. So it's going to be 4 to the n minus 1. So we have to kind of get comfortable playing around with exponents and thinking about, you know, how I can slightly modify. Can I add 1? Can I subtract 1 to make it work out? So now, again, if I plug in 1, which is how I define a sequence, I have to start by plugging in 1. 4 to the 1 minus 1 is 4 to the 0. Then I'd plug in 2. So 4 to the 2 minus 1 will give me 4. Then we plug in 3. This is the third term. So 4 to the 3 minus 1 gives us 4 squared, and so on. So here, this is my general term. The next thing we'll look at is a special type of sequence called a recursively defined sequence. A recursively defined sequence has the nth term, so the general term, dependent upon the value of previous terms. So let's take a look at an example. Here, write down the first 4 terms of the recursively defined sequence. So what we have in part A is we have a sub 1 is equal to 1. So we're given at least one term of the sequence. A sub 1 is 1. And a sub n, so that's the general term, is equal to n times a sub n minus 1. So when you see this, a sub n minus 1, this means the previous term. So I'm taking 1 away from the nth term, so that means the previous term. So let's go ahead and take a look at how this is going to work. So we want to find the first 4 terms. Well, we already have 1, a sub 1. So right underneath it, I'll go ahead and put a sub 2. Well, a sub 2 is equal to n. Well, n is the subscript, so that's going to be 2. And then times a sub n minus 1. So that's a sub 2 minus 1. So that's 2 times a sub 1. But like I said, that just means the previous term. A sub 1 is given as 1. So it's 2 times 1, which is equal to 2. Now we move on to a sub 3. Well, the formula is the subscript 3 is what was multiplied by, so we have 3 times a sub 3 minus 1, or 3 times a sub 2. Well, what's a sub 2? That's the previous term, so we had to find the previous term to find the next term. So we have 3 times 2, which is 6. So now, a sub 4, hopefully we kind of start to recognize the shortcut if we understand the formula. A sub 4 is just 4 times the previous term, which is 6. So 4 times 6 is 24. Now if we write these in a list, the first term was 1, then 2, then 6, then 24, and so on. And hopefully we can recognize, we've done it a few times now, this is actually a list of factorials. 1 factorial, 2 factorial, 2 times 1, 3 factorial, 3 times 2 times 1, 24 is 4 factorial, 4 times 3 times 2 times 1. So we can find the next term by multiplying by 5, and then multiplying by 6, and so on. Let's try one more recursively defined sequence. In part B, we have a sub 1 is equal to 1, so the first term is 1. A sub 2 is equal to 1, so the second term is also 1. And the general term, a sub n, is equal to a sub n minus 2 plus a sub n minus 1. So to find the general term, that's going to equal adding together the previous 2 terms. A sub n minus 2 is 2 terms back, plus a sub n minus 1 is 1 term back. So if we understand the rule, it's going to make it a lot easier to find the next term, or terms. So here we have a1 and a2, so a3. On this first one, we will apply the formula just to make sure we understand how that works. So we're doing a sub 3 minus 2 plus a sub 3 minus 1. Well, that's a sub 1 plus a sub 2. Well, a sub 1 and a sub 2 are given, so that's 1 plus 1, which is equal to 2. And so a sub 4 is again going to be adding those previous two terms. So a sub 4 is a sub 2 plus a sub 3. Well, a sub 2 was 1, and a sub 3 we found was 2. So 1 plus 2 is equal to 3. So let's go ahead and write them in a list. We have 1, 1, 2, 3. And for fun, let's just find a couple more terms because of how easy the pattern is. The pattern says you just add the previous two terms. So look, we added 1 plus 1, we got 2. We added 1 plus 2, we got 3. So 2 plus 3, our next term would be 5. 3 plus 5, our next term would be 8. 5 plus 8, our next term would be 13, and so on. This sequence actually has a special name. This is called the Fibonacci sequence. And so sometimes you'll hear or see that referenced like in movies or different things, the idea of adding the previous two terms to get the next term. Now let's move on and define a series. A series is the sum of the terms in a sequence. So remember that a sequence was a list of numbers. So in a series, we're going to add up all the terms in a sequence. A finite series is an expression of the form. So we see S sub n, so S for sum or series, S sub n is equal to A1 plus A2 plus ... plus AN. So we're adding up all those terms, right? A sub 1 plus A sub 2 all the way up to A sub n. So they're no longer separated by commas, they're all being added. So this is sort of the long way of seeing it. The shorthand way is to use what's called summation notation or sigma notation. So if we want to add up the terms A1 to AN, we can write this giant sigma notation, and on the bottom we're going to put from I equals 1, and on the top we're going to put to n of A sub I. Now the letter I here, it's written down here, the letter I is called the index of the summation. So it tells you what term in the sequence to start with. So I equals 1 means start by adding the first term, and the top value, that would be a number often, is going to tell you when to stop. So go all the way up to the nth term, and then A sub I, that's the general term. That's the general term. So again, this is a sigma, and it's referenced as sigma notation or summation notation. Now we can also have what's called an infinite series. An infinite series is an expression of the form, so we can call it S sub infinity, although that's rare. It's going to equal A sub 1 plus A sub 2 plus A sub 3 plus ... forever. So we're not going to stop at a particular value in the sequence. We're just going to add up the entire infinite sequence. So in sigma notation, we have the sum of I equals 1 to infinity of the general term A sub I. Let's look at some examples that make sure we understand sigma notation. So the instructions are evaluate the sum. Part A, we have the sum from I equals 1 to 4 of the general term I squared plus 1. So here, the notation doesn't look like the index is on the bottom, and that's just because of when typing it out, sometimes it just tries to squish it together. But we are thinking about this I equals 1 as the starting value from the sequence that we're adding, and we're going to add all the way up to the fourth term in the sequence. So we're going to add a total of 4 terms here, starting with 1, then 2, then 3, then 4. So we'll go ahead and write it out. So we're going to have 1 squared plus 1 plus, remember it's not separated by commas, we're adding, plus 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1. So now we have 2 plus 5 plus 10 plus 17. And if we add all that together, we get positive 34. So our answer to a summation is a number, a single number, because we're just adding a bunch of terms together. So here are the first 4 terms together. Example B is having us use a different indexing variable. So we have the sum of k equals 2 to 5 of the general term quantity -2 to the kth power minus 5. So different indexing variable, and we don't always have to add the first term in the sequence to more terms. We can start at any term we want. So we're starting at the second term and ending at the fifth term. So we're going to go ahead and write -2 squared minus 5 plus, then we're going to have -2 cubed minus 5 plus -2 to the 4th minus 5. And then we stop at 5. The top value is where we stop. So we have -2 to the 5th minus 5. So here we're looking at 4 minus 5, that's -1, plus -8 minus 5, that's -13. Then we have positive 16 minus 5, so that's going to be positive 11. And then -2 to the 5th, that's -32 minus 5, that's -37. And so here, if we add these all together, I'm going to get -41 plus 11, -51 plus 11, so we get -40. -40. So our sum could be a positive value, it can be a negative value, that part doesn't matter. Let's do a few more evaluating the sum. In part C, I have the sum from I equals 1 to 5 of just 3. So here on this one, I don't have that indexing variable I in my general term. So what this means is I'm adding 5 copies of 3 because the general term is 3. So that just means I have a sequence that's just 3, 3, 3, 3, 3, etc. and so on. So here I'm adding up just 3 plus 3 plus 3 plus 3 plus 3, because 3 is a1, it's also a sub 2, it's also a sub 3, it's also a sub 4, it's also a sub 5, it's every single term. The general term is a constant. So I'm adding up the first 5 terms. The index starts at 1, it ends at 5. So here I just have a total of 5 copies of 3, which is 15. So that type of problem tends to stump people, so just wanted to make sure and talk about one like that. That's just the sum of a constant general term. And then finally, let's go ahead and look at part D. We have the sum from k equals 3 to 5 of the general term 3 times 2 to the kth power. So our starting index isn't 1, it's 3, so we have 3 times 2 to the 3rd, and then plus 3 times 2 to the 4th, plus 3 times 2 to the 5th. Now the only reason I'm going over this one is because of algebra mistakes. So a common mistake is to start by multiplying the 3 and the 2 together and turning it into 6 to the k, and I cannot do that. Order of operations tells me I cannot do that. And I mean, the same thing applies when I actually have a number here. So when I evaluate each one of these, I have to do 2 to the 3rd first, right? Exponents first and then multiplication. So 2 to the 3rd, that's 8, and 8 times 3 is 24. And then plus we have to do 2 to the 4th, which is 16. 16 times 3 is 48. And 2 to the 5th is 32. 32 times 3 is 96. And here, if we add these 3 together, we end up with 168. So just make sure that you're careful with your algebra. In this example, we want to express each using summation notation. Use a starting index of either 0 or 1. So here, we're working backwards. I have this expanded notation for a series, but I want to write it in that condensed notation, that summation notation. But I have options because the starting index can be really any number we want, but here we're being told to use a starting index value of 0 or 1. As opposed to sequences, they have to be starting at 1. So here, I do want to think about how these are related to a sub 1 and a sub 2. I am adding a1 plus a2 plus a3 and so on. So I want to try to find that connection because the ideal situation would be a starting index of 1. That would be nice and easy. And this does work out nicely because how do I get 1 cubed with the starting index of 1? Well, 1 cubed, 2 cubed, 3 cubed. So this is really just a general term of n cubed or I cubed because we're trying to write this as summation notation. So if we want to use that variable I, which is typical for summation notation, and if I want to start with 1, well, the general term will be I cubed because we're going to start by plugging in 1, 1 cubed, then we plug in 2, 2 cubed, then we plug in 3, 3 cubed, and we go all the way up to 7 cubed, which makes 7 my value above the summation notation. So I have the sum of I equals 1 to 7 of I cubed. Now, this is a correct answer, that's fine. Now, just to give you some exposure, if we wanted to use a starting index of 0, how could we have done it? Well, if I want to use a starting index of 0, I still want my first term to be 1 cubed. So my general term, it can't just be I cubed because then that would be 0 cubed. So what I need is I need I plus 1 as a quantity cubed. So if I want to start with an index of 0, now this is 0 plus 1, then I'd plug in 1. So 1 plus 1 is 2 cubed, then I'd plug in 2, 2 plus 1 is 3 cubed. So now the question is, where do I stop? Well, I don't want to stop at 7 because 7 plus 1 is going to give me 8 cubed. So I have to go 1 less than that, so I'd have to stop at 6. So 6 plus 1 to the third power is my final term. So either one of these will work. And now for my second problem, I have 1 plus a third plus a ninth plus 1 over 27 plus ... 1 over 3 to the n minus 1. So here, I've actually kind of been given my general term. So 1 over 3 to the n minus 1, that's the pattern. So we can kind of see here, that will help us out. If I want to write this as a fraction, this is 1 over 1, but 1, that's 3 to the 0, 3, that's 3 to the 1, 9, that's 3 squared, 27, that's 3 cubed. So we can see here that the pattern is 3 to 0, 1, 2, 3, all the way up to n minus 1. So this one, it makes more sense to start with an index of 0 instead of 1 because I can see I have a 3 to the 0 as my starting denominator. So I have I equals 0 and I have 1 over 3 to the I. So if I start, I plug in 0, 3 to the 0 is 1, so I have my first term. If I plug in 1, I get my second term. So when do I stop? Well, I stop at n minus 1. I stop at n minus 1 because that's the last thing I plug in. Well, in I, I'm going to put n minus 1, which will give me that last term. So this one, it's like I was kind of given some help here by seeing the 3 to the n minus 1, kind of seeing that general terms form, like 3 to the something. So this is one way if I want that starting index to be 0. If I want the starting index to be 1, let's just do it for practice. So let's see, I would still have 1 over 3 to the something. I should really need to think about it here. I want that first term to be 1 over 3 to the 0. So if I plug in 1, I need to subtract 1 from I. So 3 to the I minus 1. So if I do that, 1 minus 1 is 0. Then I plug in 2, 3 to the 2 minus 1, that's 3 to the 1. Then I plug in 3, 3 to the 3 minus 1, that's 3 squared. So now it's a question of, well, where do I stop?
So I want my last term to be 3 to the n minus 1. So the very last thing I want to plug into I is n. The last thing I want to plug into that I right there is the value of n, because then I'll have the last term 1 over 3 to the n minus 1. And those are my two options given the required starting indices.